Alright, well, so far in our course we've talked about integrals that have definite limits of integration, meaning that the lower and upper limits of integration are numbers, not ideas like infinity, and we've never integrated over discontinuities that are infinite, like vertical asymptotes. So today we're going to try to extend some of these ideas that we've learned in order to accommodate sort of a wider range of applications. So what you're looking at here is the graph of 1 over x squared, and we're just going to restrict our attention to the right arm here. So we're just going to look at this right half. And what you'll notice is I've put in a couple of examples of integrals that we might be interested in. So the integral from 1 to infinity of 1 over x squared, which geometrically would amount to summing up the area from 1 all the way up to infinity. I've got the integral from 0 to 1, and that would amount to summing up all this area. And then, if we bring in the other arm, the integral from negative 1 to 1 would just include both arms. And so the question is, how can we actually answer that? Intuitively, you would think that, well, that's an infinite region, so the area must be infinite. But we're going to see that we've got some mathematical techniques that can help us to actually make sense of these and get actual numerical answers, which depend on these ideas of limits that we've come across. But what you're looking at up above are examples of what are called improper integrals. Improper integrals. An improper integral is an integral that puts its elbows on the table and that swears and doesn't say please and thank you. So I'll wait for you to stop laughing and then we'll move on. But seriously, an improper integral is a definite integral that has either an infinite limit of integration, and that would be one like we see here, the infinite limit of integration being that infinity, or that has any value from the lower limit of integration to the upper limit of integration that causes an infinite discontinuity in the integrand. So we can see here that 1 over x squared is discontinuous at 0. So that would cause, I should probably do a better job color coding, that should cause an infinite region to result. And that would be yet another type of improper integral. And then, of course, you could go. C is just an example of going from a lower limit of integration to an upper limit of integration that's in which somewhere in between you have an infinite discontinuity. And so you can take a look at the approaches we're going to take to actually answering these. Again, infinity is a hard idea for us to handle. So what we do is we basically replace the infinity with a variable. So rather than try to answer that question directly, here's 1 over x squared, we're going to put a 1 here, and rather than actually try to go out to infinity, we're going to put an a here, and we're going to get an expression for that finite region. And then what we're going to do is just going to let a go to infinity and take a look at what that value approaches. If it approaches a number, then we would say it converges to that number, and if it doesn't do that, we'd say it diverges. And B and C we'll look at in a future video, but again, you'll notice that we're basically replacing the problem, the infinite discontinuity, with a variable. So in this case, from 0 to 1 of x squared, what we're going to do is we're going to say, okay, well, I'm going to put a b here, and I'm just going to sum up this finite area, get an expression for that, but then I'm just going to let b get closer and closer to 0 from the right, and I'm going to see what that value approaches. So I'm going to do a few examples, some classic examples on the next page. Alright, let's look at this example. The limit from 1 to infinity of 1 over x squared. So as you noted on the previous page, what we're going to do is we're just going to rewrite this as the integral from 1 to a of 1 over x squared. But then we're just going to let a go to infinity. So to save on writing, I'm just going to kind of evaluate this definite integral here, and then we'll just bring the limit back in at the end. So again, graphically, here's 1. A is here. We're just going to get an expression for this blue area right here. So by the fundamental theorem, I know I can write 1 over x squared. Well, I can write 1 over x squared as x to the negative 2. So that might be a good first move. And then I'm going to use an antiderivative, which means I'm going to add 1 to the exponent. And I get this, I hope. Yep. And so then I'm going to evaluate from 1 to a. And so in doing this, I see that this becomes negative 1 over a minus negative 1 over 1, which gives me negative 1 over a plus 1. So that's an expression for this area right here. And now we're just going to bring back the limit. So the limit as a goes to infinity of negative 1 over a. And so now we've basically turned an integral into a limit. And so now, for those who are in my class, you can see why we've been studying limits for this reason here. And we know that as a goes to infinity, that goes to 0. So this is going to go to 0 plus 1, which is 1. Okay, so we're going to say that this integral from 1 to infinity of 1 over x squared is equal to 1 because that is the value that this finite area approaches as a gets closer and closer to infinity. Let's look at a few other examples. Alright, so the integral from 1 to infinity of 1 over x, notice that the graph looks very similar to the one we just did, but we're going to see something, its behavior is actually different. So again, we're going to replace the infinity with a variable, so I'm going to say the limit as a goes to infinity, and I'm going to look at the integral from 1 to a. Now it's a definite integral. So let's handle the definite integral. Well, the antiderivative of 1 over x is just the natural log of x. Now I don't need to put absolute value of x because we're only dealing with the right arm of this, so x is always going to be positive. So we'll just say x from 1 to a, and that equals ln of a minus ln of 1. And we know that ln of 1 is equal to 0. So this is equal to ln of a. And now we bring back the limit. So this is the limit as a goes to infinity of ln of a, but the natural log graph goes off to infinity as the variable goes to infinity. So we would say this diverges. Diverges. Alright, and I should have written it on the back, but the one on the previous example, the one on the previous page, we will say converges to 1. So again, very similar looking graphs, but their behavior when you sum up that area is actually different. Alright, let's look at one more example here. What happens when you've got negative infinity and infinity as your lower and upper limits of integration? Well, we still want to turn this into definite integrals, and what we get to do is we get to break this up into two integrals where we basically separate it at any x value we want. So what do I mean by that? Well, let's write this as the integral from, I'm going to write this as the integral from negative infinity to, and then you get to pick any x value you want. 0 seems like a convenient one, and it often is, but you don't have to use 0. So this is just a property of integrals I'm using here. And then I'm going to continue that integral from 0 to infinity. 1 over 1 plus x squared. And now we've basically just, this problem kind of just multiplied into two different problems, the one on the left and the one on the right. But again, we're going to replace the variables, or the limits of integration that have infinity with variables. So I'm going to take this to be, let's just say a to 0 of 1 over 1 plus x squared dx, but then I'm going to take the limit as a goes to negative infinity. And the one on the right, I'm going to call the integral from 0 to b of 1 over 1 plus x squared. But I'm going to take the limit as b goes to infinity. Alright, so let's focus on the indefinite integrals here, or the definite integrals here. The antiderivative of 1 over 1 plus x squared is tan inverse of x, and we're going to be evaluating that from a to 0. And so we'll just continue with that. That equals tan inverse of 0 minus tan inverse of a. And tan inverse of 0, the angle whose tangent is 0, well, that's 0. So that's 0 minus tan inverse of a. And so we get tan inverse of a. So we'll bring back the limit in 1 second. Let's do the right side here. Same antiderivative, tan inverse of x from 0 to b. But that's just going to equal tan inverse of b minus tan inverse of b minus tan inverse of 0. And tan inverse of 0 we know is 0. So this is tan inverse of b. Okay, and now we'll reintroduce these limits. So this becomes the limit as a goes to negative infinity of tan inverse of a. And this over here is going to become the limit as b goes to positive infinity of the tan inverse of b. Let's see if I can squish this a little bit. Alright, so now we have to think about tan inverse and how it behaves. And I know I picture the graph generally. I know that the graph of tan inverse has asymptotes at negative pi over 2 and pi over 2, and I know that it behaves like this. Right, so tan inverse as a goes to negative infinity of tan would be negative pi over 2. So this is negative pi over 2. And I would be adding that to... Ooh, I just noticed a mistake, hopefully, and this is important, so let's just fix it. Tan inverse, so I missed a negative over here. That's a negative, so this is a negative. That's important, because now I'm really taking... I'll bring this negative out. Taking the negative of tan inverse of a as a goes to negative infinity. So I get negative pi over 2. And then over here, as b goes to infinity, tan inverse goes to pi over 2. So this becomes negative pi over 2 is pi over 2 plus pi over 2, and that equals pi. So all this area in here, we sum it from negative infinity to infinity, converges to pi, which is not exactly obvious, but it's true. Alright, so there is your first type of improper integral, one where you have limits of integration that involve infinity.